Hi everyone, welcome to MyMax Academy. In this video, we'll continue with the chapter Relations and Functions, which is chapter 1 from your 12th standard CBSE Mathematics. I will continue from page number 3 in your textbook, which is definition 4, definition for equivalence relation. Last class, on the last video, we studied till the relation transitive relation, which means we studied what is reflexive, symmetric and transitive. So these types of relations we studied in our last video. So in this video we'll continue from the definition 4 in page number 3 of your textbook, so which is equivalence relation. Equivalence relation. We need to understand what is an equivalence relation. Now a relation R on a set A is said to be an equivalence relation. Said to be an equivalence relation if the relation R is relation R is reflexive, symmetric and transitive. If a relation in such a way that it is reflexive, symmetric and transitive, if it is all the three types, if it satisfies the required condition for a relation to be reflexive, symmetric and transitive, then we call such relation as equivalence relation. We call such a relation as an equivalence relation. Any relation which satisfies, which is reflexive and symmetric and transitive, is called as an equivalence relation. So we will do example 2 in your textbook. Example 2 in your textbook, page number 3 in your textbook, example 2. So what is given? So we write what is given. So given in the question is T be the set of all triangles in a plane. So T is a set T. Set T, right? Set T is defined as T is set of all triangles in a plane, which means the set T has only triangles, all different triangles which are in our plane, right? All the triangles. It can be a right triangle, it can be an isosceles triangle, it can be an equilateral triangle, it can be a scalar triangle, or it can be any triangle. So all the triangles. So what the set T has? Set T has all triangles. Then there is a relation defined on set T. There is a relation defined on this set T. That is R is defined as set of all T1 comma T2, two triangles T1 and T2. They are related if and only if T1 is congruent to T2. Obviously your T1 comma T2 will belong to the set T. So this is given. So set T is what? Set T is set of all triangles in a plane. So the set T has all triangles. Now two triangles are said to be related by this relation if the triangle T1 is congruent to triangle T2. Then we say T1 is related to T2. And obviously the triangles T1 and T2, both these triangles will come from the set T, and set T has all triangles. So this is given in the question, and what we have to prove or what we have to show. To show is, we should show that, or we should prove that R, the relation R, is an equivalence relation. Equivalence relation. We should prove that R is an equivalence relation. R is an equivalence relation. Now, proof or solution. So to prove R is an equivalence relation, we need to prove that R is reflexive, symmetric and transitive. Now I will write the definition for again all the three that we have, which are we call a relation as a reflexive relation if A comma A belongs to R for every A in set A, right? A comma A should belong to the relation R for every A in A, which means every element in A should be related to itself, right? And for symmetric, the condition is, or the definition is, symmetric relation is if A comma B belongs to R, then the reverse, which is B comma A, should also belong to R. Then we call it is true for every A comma B. Every A comma B in R, if there is an element A comma B in R, then its reverse also should be in R, and it should be true for all A comma B, for all A comma B. Then transitive. Transitive is if A comma B belongs to R and another element B comma C, wherever A comma B and the next element should start from B comma C, then A comma C should belong to R. This is also true for all ABC, right? If you are able to find any, for every pair that we can find like this, where A comma B is in the relation set R and B comma C is in the relation set R, then if you are able to find A comma C is also in that relation set, then you call such a relation as a transitive relation. So these three I had explained in details, and we saw various examples in the previous video. So you may watch the previous video to have complete understanding of these three types of relations. Now to prove R is an equivalence relations, R has to be reflexive, symmetric and transitive, which means we need to check all these three conditions, right? So the first one is, we'll check on the reflexive, to check reflexive or to prove reflexive, whatever, right? Now how do we check whether this relation is a reflexive relation? Which means A comma A belongs to R for every A belonging to A, which means for every element that we take from A. But here our A set is what? T. Here the relation R is defined on set A. Generally R is defined on set A, but here the relation R is defined on set T. R is a relation defined on set T. So we need to check that if R is reflexive. Now how do we check if R is reflective? We should prove that A comma A belongs to R for every A in T, right? Or A. So which means we have to take an element, any element from the set T, right? We are taking an element, like we are taking an element from A, and we should prove that A comma A belongs to R. So here what we have to prove, we have to take an element from T, one triangle from T, because T is set of all triangles. We'll take one triangle from T and prove that that triangle is related to itself. So which means we'll take one triangle, we'll say let T1, we are taking one triangle T1 belonging to T. See, T is set of all triangles. This T1 is a particular triangle from that set. I am taking one triangle from that set, any triangle, randomly. Let T1 belong to T, then T1 is congruent to T1, right? Any triangle is congruent to itself, right? When T1 is congruent to T1, which means when T1 is congruent to T1, if you apply this rule, T1 is congruent to T2 means T1 comma T2 is in the set R. So now T1 is congruent to T1 for all T1 belonging to T, which means for any triangle that I take from T, this condition is true. T1 is congruent to T1. So when T1 is congruent to T1, then we can say T1 comma T1 belongs to R for all T1 belonging to T. T1 comma T1 belongs to R for every T1 belonging to T. So now we have got this condition where for every A belonging to capital A comma A belongs to R. Now we compare this with this. For every triangle we are taking from the set T, the triangle is related to itself, which means T1 comma T1 belongs to R. The meaning of T1 comma T1 belonging to R means T1 is related to T1. So therefore, we can say R is reflexive. Therefore, R is reflexive, which means a reflexive relation, because we have proved this condition. Right? That is the definition for reflexive. Right? Then second one is we have to check whether it is symmetric. So to check symmetric, which means whether R is a symmetric relation. Now for R is symmetric relation, what we should check? We should check first to take one element from the relation R, and we should show that the reverse is present in that relation. So first thing requirements, we should take an element from, not from A. We took an element from A, or here we took an element from T, that was for reflexive. For symmetric, we should take an element from R. So we will say let T1 comma T2 belongs to R. I am taking one element from R. Now what we should prove? We should prove the reverse is in R. We should prove T1 comma T2 belongs to R. Right? Sorry, T2 comma T1 belongs to R. So we have taken T1 comma T2 belonging to R. So we took an element from R, which is T1 comma T2, and we should show the reverse. Reverse is T2 comma T1 should belong to R. That's what we have to prove. Now so if you want to prove T2 comma T1 belongs to R, means we should prove T2 comma T1. T2 is congruent to T1. If T2 is congruent to T1, then we will say T2 comma T1 belongs to R. Right? So to prove that, now this is, so we have taken one element, one ordered pair from R. We should show the reverse is in R. If we show that, then we can say R is symmetric. Fine. Now when T1 comma T2 belongs to R means what? As per the definition, T1 is congruent to T2. So T1 is congruent to T2. The triangle T1 is congruent to T2. Now whenever T1 is congruent to T2, we can always say T2 is congruent to T1. Right? If there are two triangles, if one triangle is congruent to other triangles, then we can say the reverse way. Right? If I say triangle A is congruent to triangle B, we can say triangle B is congruent to triangle A also. Right? So we can say T1 is congruent to T2, which means this implies T2 is congruent to T1. Right? So whenever T1 comma T2 belongs to R means it implies that T1 is congruent to T2 as per the definition. Then when T1 is congruent to T2, the reverse is true, which means T2 is congruent to T1. Always, whenever a triangle A is congruent to triangle B, then we can say B is congruent to A. Right? So which means T2 is congruent to T1. Right? Then, so therefore, so we can say when T2 is congruent to T1 means, now this we have got this definition. T2 is congruent to T1 means T2 comma T1 belongs to R. So T2 comma T1 belongs to R. This implies, because we got this definition. Whenever this is true, you can say this ordered pair is in relation R, relation set R. So we have got T2 is congruent to T1. Therefore T2 comma T1 belongs to R. Now we need to, therefore we can say, so I'll write it here. So therefore we can say, therefore R is symmetric. R is symmetric because we took an element T1 comma T2 in R and we showed that the reverse, which is T2 comma T1 is in R. Therefore it is a symmetric relation. Now we need to check for transitivity. The third one is, this is first one, second one, and third thing that we should check is, we should check transitivity. To check transitivity. To check transitivity. Now how do we check transitivity? Transitive we can say. To check transitivity is also fine. To check transitive. So what do? We should take two elements from the set R in such a way, A comma B, then it should start from B comma C. So we will say let T1 comma T2 belong to R and T2 comma T3 belongs to R. Right? This is like A comma B and B comma C. Here A is T1, B is triangle T2, again B. So T2 again, then C is triangle T3. So if we have such two pairs, if we have such a pair in relation R, we should prove that T1 comma T3 belongs to R. If we can prove T1 comma T3 belongs to R, we can say it is transitive. So this is there. If we have these two elements in R. If these two elements are present in R, then we should prove that A comma C means T1 comma T3 should be in R. We have to prove that. If we prove that, then we can say that R is transitive. Now, for that we will say T1 comma T2 belongs to R. So which means from this, when T1 comma T2 belongs to R means what? This implies T1 is congruent to T2. Right? Whenever T1 comma T2 belongs to R means T1 is congruent to T2. I can write this definition. If this element is present in R means I can write this definition. If this definition is true means I can say T1 comma T2 belongs to R. Right? It's either case, if and only if. Now similarly T2 comma T3 belongs to R. So this implies that your T2 is congruent to T3. When T1 comma T3 belongs to R means your T2 is congruent to T3 as per this definition. When I say T2 comma T3 is in R means T2 is congruent to T3. Now T1 is congruent to T2 and T2 is congruent to T3, which means we can say as per the rule of triangle congruency, if T1 is congruent to T2 and T2 is congruent to T3 means we can say this implies T1 is congruent to T3. We can say T1 is congruent to T3. So therefore, now what we got? Therefore, we have got when T1 is congruent to T3 means I have got this definition. Sorry, whenever we get this definition, we can say this. We can say T2, T3, we can say as per this definition, T1 is congruent to T3 means what? Sorry. T1 is congruent to T3 means T1 comma T3 is in R. Therefore, T1 comma T3 belongs to R. Or we can even say this implies if you want. This implies T1 comma T3 belongs to R. Because whenever one triangle is, if a triangle A is congruent to B and triangle B is congruent to C, then we can say triangle A is congruent to triangle C. Or if triangle 1 is congruent to triangle 2 and triangle 2 is congruent to triangle 3, then you can say triangle 1 is congruent to triangle 3. That is always true for congruency of triangles. Right? So therefore, we got this condition T1 is congruent to T3 means I can say T1 comma 3T belongs to R. So therefore, R is transitive. So R is a transitive relation also. Then conclusion is, since we have proved that all the three, since R is reflexive, symmetric and transitive, therefore R is since all the three conditions are met. So whenever a relation R is reflective, symmetric and transitive, then we can call that as an equivalence relation. Therefore R is an equivalence relation. Okay, so this is how we prove that R is an equivalence relation. Clear? So you can pause the video and take the notes. I will erase and we'll move to example 2. Sorry, example 3. We'll go to the next example. This was example 2. We'll go to example 3. Erasing this. So what is example 3? Again, example 3 it is given as example 3 in your textbook. LB set of all lines in a plane. L is what? L is set L. Set L is set of all lines in a plane, which means this L is a set which has all lines in the plane. Any line. So the plane means what? It's a 2-dimension, right? So all the lines, this line, this line, this line, the y-axis, x-axis, x dash, even the axis will also be there. This is also a line. All these lines will be there. All lines will be in this. So L is set of all lines in a plane. Now what is the relation defined on that? The relation R is defined as L1 comma L2, which means line 1 and line 2 are related. If we can say L1 comma L2, L1 is related to L2 if L1 is, or if and only if L1 is perpendicular to L2, which means two lines are related if they are perpendicular to each other. L1 is perpendicular to L2 means we can say L1 is related to L2. Obviously the L1 and L2 they will come from the set L. That is obvious, right? We can say comma L1 comma L2 both come from the set L. That is understood even if they have not given that. That's why they have not mentioned that in the book, right? So which means the line L1 and L2 belong to L. Fine. L1 is perpendicular to L2 and L1 comma L2 belongs to L. Now we should show what we have to prove. So these two are given. So this is given in the question. So given, these are the given things in the question. The given is these two. Right? Both are given. So I'll write the given here. Given. Given is L is set of all lines in a plane and relation R is L1 comma L2 such that L1 is perpendicular to L2. L1 is perpendicular to L2. Now we should show that R is symmetric but neither reflexive nor transitive. So what we should show that what we have to show? We have to show R is symmetric. First one, what we have to show? R is symmetric. We have to show. Or we'll say first one R is. We say R is symmetric, but neither reflexive nor transitive. We should show R is not reflexive. Second is we should show R is symmetric. And third one is R is not transitive. So this is what we have to prove, or we have to show that, right? The first is we should show, so proof or solution. So solution or proof we can say. So what it means is we have to prove that first R is not reflexive. We have to prove that R is not reflexive. Now then we should take one element from set A. Here our set A is L. So we'll take an element from L. L is what? L has only lines. So any element that I take from the set L will be a line. So we'll say let L1 be L1 belong to L, which means I am taking one line L1 from the set L. So this is an element, it's a line, and this L is a set of all lines. I am taking one element which is a line from the set of all lines. One line I am taking from the set L. Then L1 is not perpendicular to L1 because a line cannot be perpendicular to itself. A line cannot be perpendicular to itself. A line is parallel to itself. In geometry, we can say a line is parallel to itself. A line cannot be perpendicular to itself. Right? Suppose if this is your L1, your line L1, I cannot say L1 is perpendicular to the same line L1. I can't say this line is perpendicular to itself. Right? So L1 is not perpendicular to L1. Therefore, if it is not perpendicular, then which means L1 comma L1 will not be, does not belong to R. For any L1. For any L1 belonging to L, for any line L1 from L, you cannot say L1 is perpendicular to itself. The line cannot be perpendicular to itself. For reflexive, what the condition is? A comma A should belong to R, which means if I take an element, this is your small a. If you compare this with this, A is here, so this is my small a. So any element that I take from the set A, here the set is L. right? Then I should prove L1 comma L1. If L1 comma L1 belongs to R, we can say R is reflexive for every L1 in L. But we see that for that, to prove that L1 is related to L1, we should prove L1 is perpendicular to L1. To prove L1 comma L1 belongs to R, I should apply this. We should get this condition. What is the condition? If L1 comma L1, if both are L1, means L1 is perpendicular to L1. We will get L1 is perpendicular to L1. L1 is not perpendicular to L1. A line cannot be perpendicular to itself. So it is not reflexive. Therefore, R is not reflexive. Reflexive relation. Now, second part. So this is the first part. Second part is we should show that R is symmetric. We have to prove here. So to prove R is symmetric, what we should take? We should take one element from R, right? We will say let L1 comma L2 belongs to R. We are taking one element from R, and what we should prove? For symmetric, we should prove the reverse is in R, which means we should prove L2 comma L1 belongs to R. To prove L2 comma L1 belongs to R, we should prove that L2 is perpendicular to L1. We should prove L2 is perpendicular to L1. Now we have started, so we should take the element. So to prove it's a symmetric relation, how do we start? Always is we'll take one element from the relation, right? And then we should prove the reverse ordered pair is in that set R. Now let L1 comma L2 belongs to R. We should prove now L2 comma L1 belongs to R. Then that will make R as symmetric. Now when L1, this is true. This we have taken an element. L1 comma L2 belongs to R means what? L1 is perpendicular to L2. This is the meaning. This is symbol for perpendicular. L1 is perpendicular to L2. That is the meaning of L1 comma L2 belonging to R means what? L1 is perpendicular to L2. When L1 is perpendicular to L2, we can say L2 is perpendicular to L1, right? Because if there is another line, suppose this is perpendicular to this is a line L2. Suppose we can say L1 is perpendicular to L2. I can also say L2 is perpendicular to L1, right? I can also say L2 is perpendicular to L1. So we can say if L1 is perpendicular to L2, we can also say L2 is perpendicular to L1, right? This implies this. So this implies when L2 is perpendicular to L1, L2 is perpendicular to L1. What it means? If L2 is perpendicular to L1, then L2 comma L1 will belong to R. So this implies L2 comma L1 belongs to R. Now we started with L1 comma L2 belonging to R, and we have proved L2 comma L1 belongs to R. Therefore, R is symmetric. R is symmetric. Symmetric means symmetric relation. Now we should, the third one is we have to show that it is not transitive. Let's show that it is not transitive. So the third part, so I'll do it here. Third part. Third is we should show that R is not transitive. To show R is not transitive, we should take two elements from R. Sorry, this belongs to R. Should say this also belongs to R. Right? B comma C belongs to R. Then we can say A comma C belongs to R. Okay. So the third one is we should take two elements from R. That is the starting of the proof for transitive. You should take two elements in such a way from R, then you should show that A comma C belongs to R. The third element A comma C should belong to R. Now let's take two elements. So how do we take this? So we'll say let L1 comma L2 belongs to R, belongs to L. Sorry, R is a relation. R. We are taking from the relation. And L2 comma L3 belongs to R. So we are taking two elements like this. A comma B, B comma C. Here A is L1, B is L2, again B is L2, C is L3. So we are taking two elements from R in such a way that L1 is perpendicular to, L1 is related to L2, which means L1 comma L2 belongs to R and L2 comma L3 belongs to R. When L1 comma L2 belongs to R means what? L1 comma L2 belongs to R means this implies that L1 is perpendicular to L2. That is the meaning of this. And again, L2 comma L3 belonging to R. This implies your L2 is perpendicular to L3. Right? Whenever you say this element is in R means this condition is true. If this condition is true, then you can say L2 comma L3 belongs to R. So here L2 comma L3 is in R, which means L2 is perpendicular to L3. Similarly, L1 comma L2 is in R, which means L1 is perpendicular to L2. Now it looks like this. If I try to put this condition diagrammatically, right, then we get like this. L3. See, your L2 is perpendicular to L1, your L2 is perpendicular to L3. L1 is perpendicular to L2 and your L2 is perpendicular to L3. Then therefore what happens to L1 and L3? Is L1 perpendicular to L3? No, L1 becomes parallel to L3. So this implies, these two implies L1 is perpendicular to L2, L2 is perpendicular to L3 means L1 is parallel to L3. L1 will become, if L1 is perpendicular to L2 and L2 is perpendicular to L3 means what? We cannot say L1 is perpendicular to L3, we can say L1 is parallel to L3. See, both will become parallel. This is line 1, this is line 3, this is line 2. This is your line 2. This is your L2. This is your line L2. Right? So L1 is perpendicular to L2 and L2 is perpendicular to L3, but that makes your L1 parallel to L3, which means L1 is parallel to L3 means what? This implies L1 is not perpendicular to, but for L1 comma L3, so what we have to do? We have to check whether L1 comma L2 belongs to R, L2 comma L3 belongs to R means we should prove L1 comma L3 belongs to R. If you prove L1 comma L3 belongs to R, all become transitive, but here we should prove that it is not transitive, which means we should prove that L1 comma L3 does not belong to R. You have to prove that L1 comma L3 does not belong to R, which is true because L1 is not perpendicular to L3. If L1 is not perpendicular to L3, then L1 is not related. Then L1 comma L3 will not be in this set, which means this implies your L1 comma L3 does not belong to R because your L1 is not perpendicular to L3. Therefore, it will not be in R. For L1 comma L3 to be in R, we should, if L1 is perpendicular to L3, then L1 comma L3 will be in R. If L1 is not perpendicular to L3, then L1 comma L3 does not belong to R. So now we got two elements like this, but the third element L1 comma L3, it is not in R. Therefore, it is not transitive. If L1 comma L3 is in R, then it will become transitive. But here we got L1 comma L3 not in R. Therefore, R is not transitive. We will say therefore R is not transitive. That is the proof. So we have showed that it is not reflexive, but it is symmetric and not transitive. Fine. So you can all pause the video and take the notes. I will go to the next example, example 4. So example 4 is, and so we'll write what is given. So what is given? Show that the relation on the set 1, 2, 3. So there is a set given. So given is, I'll write set A. I'll probably write it here. Suppose given. What is given in the question? For example 4, given is R is a relation on set 1, 2, 3. We'll call that set as A as 1, 2, 3. The set name is not given, but I am taking it as A. And R is a relation. And what relation is defined on that? Relation is equal to 1, 1, 2, 2, 3, 3, 1, 2, and 2, 3. It's a relation. Okay, it's a subset of A cross A. Right? And we should show that. So what we have to prove? To prove or to show, what we have to prove is, first one is R is reflexive. Second one, R is not symmetric. But neither symmetric nor transitive means R is not symmetric. Third one we have to prove is R is not transitive. R is not transitive. So we need to show these three for this relation. It is on the set, this one. Now first one, the solution or proof, whatever. Right? We have to prove R is reflexive. Now R will be reflexive what? Whenever this condition is set. So for every A in A, one A comma A should be in R, which means for every element that we take from A, right, it should be related to itself. Which means if I take an element 1 from A, then 1 comma 1 should be in R. Is it there? Yes. If I take the element 2, then 2 comma 2 should be in R. It is there? Yes. If I take the element 3 from the set A, 3 comma 3 should be in R. Yes. So every element that we take from A, the ordered pair, the element with itself, 1 comma 1, 2 comma 2, 3 comma 3. Suppose if A has 4, then 4 comma 4 also should be there. Here A does not have 4, but I'm saying if in case if there was a 4 here, then we should be having 4 comma 4 also here. Then only it will make it as a reflexive. Now anyway, here we have only 3 elements, and all this 1 comma 1, 2 comma 2, 3 comma 3 is there in C. So we'll say we see that 1 comma 1 comma 2 comma 2 comma 3 comma 3, all these are belonging to R, right? Every element 1, 2, 3 in A, its pair is related to it's present in R. So we see that 1 comma 2 related to R. Therefore we can say A comma A belongs to R for every A belonging to set A. So we have got that condition. For every element that I take from A, if it is A is 1, then 1 comma 1 should be in R. It is there. If A is 2, then 2 comma 2 should be in R. It is there. When A is 3, then 3 comma 3 should be there. Yes. So therefore we can say R is reflexive. Therefore we can say R is reflexive. Fine. Then, so this is for the first part. The second part we should prove that it's not symmetric. Second part. See, whenever you have only minimal, less number of elements here in the relation R, then you can individually validate whether it is reflexive, symmetric and transitive by taking the elements from R. Right? If all the elements satisfy the condition, then we can say it is reflexive. Even if one element fails, we will say it is not reflexive. Here all the elements are satisfied. For every A, it is true. Right? So second one is R is not symmetric. So we will say to prove R is not symmetric, what should we do? We should take one element A comma B from R, and we should say the reverse is not in R. We should show that the reverse is not in R. If we show that the reverse is not there, means it is not symmetric. So we'll take an element. We'll say let's see this 1 comma 2. It is in R. Is the reverse in R? 1 comma 2's reverse is what? 2 comma 1. That is not there. So therefore it is not symmetric. So we'll say will not let the element is present there. So we have 1 comma 2 belonging to R, but 2 comma 1 does not belong to R. Therefore R is not symmetric. That's it. Even if it fails for one element, even if it fails for one of the elements in R, we can say that that relation is not symmetric. It should be true for every element. See here, if you take 1 comma 1, reverse of this is 1 comma 1. So it is true for this. 2, reverse is 2 comma 2. It is there. 3, reverse is 3 comma 3. It is there. For 3 comma 3, reverse is 3 comma 3. For 1 comma 2, reverse is 2 comma 1, which is not there. So it is failing. So you stop here. Don't need to check the next element. Stop here and say it's not symmetric. Fine. Now the next one, which is third one. Third one is we should prove that it is not transitive. We should prove that it is not transitive, which means we should take two elements such as A comma B, and second element should start from B. Wherever the first element is ending. First element is ending with B means second element should start from B, then another element C, then A comma C should belong to R. To prove that it is not transitive, we should show that if I take A comma B belongs to R and B comma C belongs to R, we should show that A comma C does not belong to R. Then it becomes not transitive. Now let's take the element. Let's observe these two elements. Erasing all this. Let's observe these two elements. 1 comma 2 belongs to R, right? And 2 comma 3 also belongs to R. This is like A comma B, B comma C. A comma B, B comma C belongs to R. So A comma B belongs to R and B comma C belongs to R. But A comma C, what is A comma C? 1 comma 3. But I can write Okay. Take 1 comma A comma B belongs to R, B comma C belongs to R, but 1 comma 3, which is A comma C, does not, or we can say does not symbol, but this does not belong to R. Therefore, R is not transitive. Even if it fails for one of the pairs. Even if it fails for one of the pairs. So this pair of elements, this is A comma B, B comma C. This is like A comma B, B comma C. So this is like A comma B, B comma C. So but A comma C means 1 comma 3 is not in R. If it is in R, then we will say this. If it is in R, then we will check for other pairs, whether it is true for all the pairs. If it is true for all the pairs, we will say it is transitive. Even if it fails for one of the pairs, we will say that the relation is not transitive. So here it is failing because 1 comma 2 is there in R, 2 comma 3 is there in R, but 1 comma 3 is not in R. Therefore, it is not transitive. Clear? So this is how we check or we try to see whether the given relation is reflexive, symmetric and transitive. So you all can pause the video and take the notes. I will stop the video here and you can watch my next video for the continuation of this. Thank you for watching. See you in the next video.